Good morning, guys. I hope you are doing okay. Yesterday, in the last class, we have discussed about column base, that is the normal slab-based design, gusset-based design, the principles of designs, and we have done some examples through that. I hope you all understand that. If you have any questions, please feel free to ask. Today, you will be starting a very important module, very important module, because this module do not follow the IS code. That means in IS code there is nothing written basically on for this module. This is the eccentric connection. That means when a eccentric load is acting on a member, the eccentric connection, that is then the member will be subjected to shear force as well as bending moment. Consider if this is a member beam, a load is acting here at a distance L. So at this point there will be shear force plus bending moment. So up to now, in the design of the connection, that is bolt connection, weld connection, we have analyzed the connection. We have designed the bolted connection or the welded connection based on the axial force, that is the force that is axial. But in the eccentric connection design, we will be designing the connection with combined action of shear force and bending moment. So eccentric connection is very much important. In eccentric connection, if in the picture you can see it's like a eccentric connection. If this is consider this is a column and this is a beam. So in case of steel building that we have discussed, we have done beam design, we have done column design. So at the junction of beam column design or beam design, two beams may be connected to each other, or a beam may be connected with the column, like this picture. So for that, the beam to column connection are expected to resist end reaction are termed shear connection. That means this is a end reaction which is acting at the end of the beam. Okay, so end connections or the end reactions, so they are called shear connections. So this is the first type of connection, shear connection. Then comes another type of connection, when in another type of connection, so here you can see the connections in which the connection which is only to be expected to transfer end reaction, they are called the shear connection or the flexible connection. Now if this is the picture of the flexible connection or the shear connection, here you can see the beam, it is the beam, here it is a flexible connection. Only two angle sections are used to connect the beam members. The load will maybe acted here. Okay, so the end reactions are only here. So this is called a flexible connection. There may be some connections where the relative rotation, okay, in case of the flexible connection, here as it is bolted connection or it may be welded connection, so based on that there may be some rotation in case of flexible connection in the beam column junction. But there are some connections where this type of connection where there cannot be any rotation at this junction because it is fully braced. This is one, and this is one. So this section is fully braced. That means this section cannot permit any rotation of the beam column junction. That means this column at this connection, it is subjected to both shear and bending. So this connection is called moment or rigid connection. Then comes another connection like this semi-rigid connection. In semi-rigid connection, there is relative rotation between the beam and column connection, but also there is relative rotation between the beam and column connection, but also it permits the relative rotation, but it is also subjected to shear and moment. So this is called semi-rigid connection. So in the flexible connection, the beam column junction is only subjected to end shear force. In the moment or rigid connection, it is subjected to moment as well as the end reaction, and there is no any movements or there is no any rotation between the column and beam junction. And in the semi-rigid connection, relative rotation between the column and beam, relative rotation is permitted between the column and beam joint or the beam joint, and it is also subjected to end reaction as well as moment. So throughout our lecture, as per our syllabus, we will only study the flexible connection. Okay, we will only study the flexible connection. So today we will be studying bolted flexible connection. In the next lecture, we will study welded flexible connection. So bolted flexible connection we will study now. Now the connections subjected to eccentric shear are generally three types: framed connection, seat connection, and bracket connection. We will be discussing what are frame connection, what is seat connection, what is bracket connection. So the first line is only eccentric shear. That means only end reactions are acting in case of this moment flexible connection. There is no moment in case of any flexible connection. So the member is subjected to only end shear, end reaction force. So we will be designing the member based on that. So coming to the framed connection. In case of framed connection, this is the number A. This is the frame connection. The frame connection, you can see the picture. The first one is a column beam connection. Second one is a bolted beam connection. In case of the column beam connection, the beam, this is the connecting beam. This is the connecting beam. It is connected with the column flange. It is connected with the column flange. It is called frame connection, column beam connection. The beam is connected with the column flange. As we are first discussing today is the bolted connection. Today we will be discussing about only bolted. We will not be discussing welded. We will discuss the welded connection in the next class, in the next lecture. Okay, so we will be discussing only the bolted connection. So here, this is the bolted connection. Now how to connect the beam with the column? Also, in case of the beam connection, this is one beam or the beam girder, this is another beam. Okay, so these two beams are connected. Now how to connect this beam with the column flange or the beam with another beam? With the help of this framing angle. With the help of this framing angle. These framing angles are here to connect the beams with the column or the beams with the beams. So in the framed connection, our motto will be, what we will have to find out? The size of the connection and the design of the bolt that are used in the connection. So we will be designing the framed connection first. So this is the framed connection. Okay, so please listen carefully and understand then very carefully that a framed connection, when a beam with a column or a beam with a beam are connected with the help of framing angles. Here framing angles are used to connect the beam with the column or the beam with the beam. Now coming to the design procedure of framed connection. The first procedure is the end reaction which the beam is subjected to is computed. That means the end reaction, that is the load that is acting at a distance. That means if it is an end so the load that is acting, this is the end connection. It is termed as R. Okay, this is R. So the end connection is first computed. This is the first step. Next step, connection of the framing angle with the wave of the connecting beam is designed, or the connection of the framing angle with the wave of connecting beam is designed. That means this connection has to be designed. This is the connecting beam. This is the connecting beam. Okay, this is the connecting beam. The connection with the column plane, this connection, the connection for the wave, the connection for a framing angle with the wave of the beam is designed. Now how to design that? First we have to assume the dia of the bolt. That means which will be the dia of the bolt that is assumed. Then the pitch and the gauge distances are assumed. We know how to assume the pitch and gauge distance. If you can recall, we have done this in the bolted connection, how to assume the pitch and the gauge distances. Then the minimum pitch and minimum gauge distance, how to assume. From there we have to assume the pitch and gauge distance for the connection. Then the strength of the bolt is calculated. But here you know the strength of the bolt is calculated based on strength of the bolt in shear and strength of the bolt in bearing. Now as the strength of the bolt in shear, here it will be double shear. Why it is double shear? Because of this section. Why it will be in double shear? If we draw this picture here, this picture to be drawn here, so you can see this is one leg of a framing angle, this is another leg of a framing angle, and this is the wave of the beam that to be connected. So one plate, another plate, so three plates are connected together. It is acting as a lap joint. For a lap joint, always it stay in double shear. Always it stay in double shear. Okay, always it stays in double shear. So strength of the bolt in double shear and bearing is computed, and the number of the bolts required for this connection, number of the bolts required for the connection are determined by this condition: end reaction divided by the strength of the bolt. The end reaction that is acting, that is the R value that we have taken, divided by the strength of the bolt in shear or bearing, which is the lowest value we have to take. Then the strength of the bolt is connected. Here it is also shown that a double shear as butt joint. So as there is butt joint, so double shear will be provided. So it will be butt joint, not lap joint. So butt joint it will be provided. Now this is the step number 2. Coming to the step number 3, connection of the other leg with the framing angle with the girder is designed. That means now we have to design that part. Now we have to design this part. Okay. Now we have to design this part. So the connection of the other leg with the framing angle with the girder is designed. So the girder have to be designed. Now dia of the bolt, similar procedure. Dia of the bolt is assumed along with the pitch and the gauge like the first step. Then the strength of the bolt in single shear and bearing is computed. Now why it is single shear? Because if you see here, if you see in this picture, okay, let me that. So if you see in this picture, that joint here, it is like that. It is one plate and this is the angle section. It is connected throughout. So here is it is only lap joint. So only single shear will be acting. So the single shear. So single shear and bearing has to be calculated. Then the strength is calculated. The lowest of that we have taken. Then N dash, that is the number of the bolt for connection to the wave of the girder to the framing angle is determined. That is the N dash equals to N reaction by the strength of the bolt. That is the formula. So the number of the bolts for both the connections. One connection is the one leg with the wave of the connecting beams, and another connection is the one leg with the column flange or the beam girder, that depending on the section that we provided. So this two connection has to be, number of the bolts are to be designed. Now comes the design of the angle, the selection of the angle section. Depending on the number of the bolt and pitch and gauge length, size of the framing angle is determined. So we have got the pitch and the edge distances. Pitch and edge we know. So if we put the pitch and edge in a line, in a row, so we can got the minimum length required for the framing angle. So we can find out the minimum length required of the framing angle. So after the minimum length required by the framing angle is calculated, so the size of the framing angle can be determined. But the most important part that is left is the thickness of the framing angle. How to determine the thickness? It is very easy. In the fifth step, now the thickness of the angle can be computed by equating the end reaction with the shear strength of the angle length. Now, how to determine the shear strength of the angle leg? By this formula. Vd equals to Fy by root 3 gamma m0 h into 2 into Tw. H equals to depth of the framing angle, that we have determined what is the depth of the framing angle, and Tw is the thickness of the angle to be determined. Now we have to find here the Tw, that is the thickness of the angle to be determined. Okay, now there comes the question, why it is 2 into Tw? Because there are always two angles are generally provided. If you see the picture, here it is one angle, in that face, in this face there is another angle. Similarly here also in this face there is another angle to be provided. So depending on that two angles, for two angles the shear strength has to be taken 2 into Tw. From there the shear strength, depending on the shear strength. Now what is the shear strength? Now the shear strength Vd will be equals to the reaction force, because the thickness has to be such that it can resist that much reaction. So depending on the reaction we have to design the shear thickness. So this is the design procedure for designing of the framed connection. Now we will see one example for that. Consider this is the one ISLB 300 transmit an end reaction of 385 kilonewton to the wave of ISMB 450. Okay, design the bolted framed connection steel grade atho to atho. Now if we see the picture, it will be like that. So by this question we can assume that this is the ISLB section which is connected to the ISMB section. So this is the girder and this is the connecting beam. So we have to design for that. So first the end reaction, that is step 1. Now coming to, let us use another page here like that. Okay, so I have opened another window where the one window the mat will be there, and another window the process we can see and correlate with each other. The design procedure, first is the end reaction with the beam is computed. So the end reaction is 385 kilonewton, that we know. So end reaction is 385 kilonewton, that we know. Now so then we will write down all the properties of the section, that is ISLB 300 and ISMB 450. We will use the ISSP 6, that is the handbook for steel design we will use, and all the properties of these two members are to be written from that IS handbook. Now coming to the step 2. What is step 2? Here the step 2, connecting of the frame angle with the wave of the connection beam is designed. That means first we have to design this connection. So all the procedure will be followed. The diameter of the bolt is assumed. So first assuming 20 mm diameter bolt for the connections. Then so the D0 will be, that is the diameter of the hole, will be 20 to 20 plus 20 to 22. A and B, that is the area of the fastener, that is the area of the hole, is 245 millimeter square. If you can recall the value, I have written in the I have given the chart for the calculation of the A and B for each bolt dia. This is the value. Then the minimum E, that is the edge distance, for that is equal to 33 mm. From the chart that value is also given, that is 33 mm, and pitch equals to 2.5 into 20, that is the 2.5 times the diameter of the hole, diameter of the bolt. So this is 33, taking the value to be 40, this is 50, taking the value to be 60. So this edge and pitch distance we will provide. Now what is that? The strength of the bolt in double shear to be calculated. So strength of the bolt in double shear 2 into that value. So we are getting this, and strength of the bolt in bearing. So bearing, to calculate the bearing we have to find out the KB, that is the KB value. So KB is smaller of, you know, that is E by 3D0, P by 3D0 minus 0.25, FU, B by FU, and 1.0. So from all that the value to be 0.61. The value to be 0.61. Okay, sorry, here one thing will be changed. It will be 0.61. The lowest value to be taken, so it will be 0.61. Okay, So 2.5 into kb into d into t into fu by K. So kb value we have got 0.61 because this is the lesser value. So we will take that value. Now coming to the formula of t. So which t to be taken? Now we do not know the T of this angle section. We only know the T of this connecting beam. So connecting beam means ISLB 300. So ISLB 300. For that, the TW, that is the thickness of this wave. Thickness of this wave connection, that is this wave connection. Thickness of this wave connection is 6.7. So putting that value here, 6.7. VTBB, we have got 67.03 kilonewton. Now strength of the bolt in bearing is equal to 67.03 and strength of the bolt in double shell 90.528. So which value to be taken? The lowest value. So the strength of the bolt will be 67.03 kilonewton. Then coming to the number of the bolt. So number of the bolt's formula. Next procedure is the number of the bolt is calculated end reaction by the strength of the bolt. So end reaction by the strength, that is equal to 5.74, taking it to be 6 knots. 6 numbers of bolt to be taken here. So 6 number of bolts for the connection of the framing angle with the wave of the connecting beam. Similar procedure to be followed for the framing another connection, that is the framing angle with the connecting girder or the connecting girder. So similarly all the process will be followed. So step 3 we are following now. Assuming 20 number of dia bolt. So for 20 number of dia bolt, this value this edge and pitch distance will be taken also. So for that, strength of the bolt in single shear, as it will be single shear, that I have told you why it is be single shear. So single shear strength is calculated, then the strength in the bearing is calculated. So both values are put here. So we have got the strength of the bolt in single shear, that is to be 45.264, and strength of the bolt in bearing to be 94.038. So what value to be taken? That is 45.264. Now here also when we are calculating the thickness of the girder will be taken, because we do not know the thickness of the framing angle. We will take the thickness of the girder, that is the thickness of this girder. So this thickness of the girder to be taken. So thickness of the girder we have got, that is ISMB 400, it is to be 9.4. So putting this value to be here, 9.4 mm, we have got 94.038 kilonewton. So number of the bolt will be that by that is equal to 9 number of bolt. So providing 3 rows of 3 number of bolts. So 3 rows of 3 numbers of bolt will be provided. Now coming to the step number, next step, that is depending on the number on the bolt, pitch and gauge, the size of the framing angle is determined. So this is the size of the framing angle. So this is the connection with the this angle, this leg is connected with the girder and this leg is connected with the beam. So for the beam, number of the bolts are 6 now. So 6 number of bolts are provided in 2 rows, and for this leg 3 numbers of bolt provided in 3 rows. So 3 number of bolt provided in 3 rows. So size of the one leg will be, first this leg, this to be 40 plus 60 plus 60 plus 40. So 2 into 40 plus 2 into 6, that is equal to 200. Okay, and taking it to be 200. Now size of the another leg, that to be 2 into 40 plus 60, that is from that 40 plus 60 plus 40, that to be 140, taking the value to be 150. Now what angle to be selected based on that? Let us open SP6. So it is to be a unequal angle. So putting this value here, if we see the portion of the unequal angle, okay, let us go to unequal angle like this. Okay, this is the unequal angle. So we can see 250 are the one legs. So this is to be the angle. 200 into 150, we are taking this angle values. Now we do not know which thickness to be taken. We do not know that which thickness to be taken. So we have to determine the thickness. That is in the next step, determine the thickness. So providing 2 forming angles of 200 into 150 size. Now we determine the thickness. The thickness of the angle, V is equal to VD, that is equal to R is equal to that value. So V is equal to VD, that means V is equal to the R, that is the value of the reaction that we have know. Then putting all the values, 2 into TW we have to find out, putting all the values. H is the height, that is the length of the higher value. So this is we are taking as the H. The higher value is taken here, that is equals to H. Putting all the values, we are getting 6.98. So we can take 8, so 6.98. So the lowest value of the thickness for that angle to be 10 mm. So 202 forming angles of 200 into 150 into 10 mm are taken. So this is the design and the design procedure and the design of the framed connection. Okay, so we have designed the framed connection. For the eccentric connection, we have designed a bolted frame connection. Now coming to the next connection, that is the seat connection. What is a seat connection? Now we will discuss seat connection. What is the meaning of seat? Here, in case of a seat connection, what is basically done, it is also a beam to beam or beam to column connection, but here the beam is connected with the column flange or the girder with the help of a seating angle. A seat angle is provided so that the connection can be made. Okay, the beam, the surface of the connecting beam is rest on the seating angle, which is used for the correct positioning of the beam. By providing the seating angle, the correct positioning of the beam can be provided. Okay, if we see the picture here, this is two type of seat connections are generally provided: unstiffened seat connection. What are the difference? I will tell you. If we see the unstiffened seat connection, we can see here, this is the beam, connecting beam, and this is the column flange. It is written here, connecting beam and the column flange. This beam rests on this seat angle. This beam rests on this seat angle. Okay, so the seat angle is provided so that the beam rests on the seat angle. Now, for lateral support, to give the beam lateral support, another angle is provided, that is the cleat angle. This is the cleat angle. This is provided so that the beam cannot move laterally. So lateral support is given by the cleat angle. In the design of the seat angle, it is the seat connection, it is assumed that the cleat angle that we are using do not carry any load. So there is no need to design the cleat angle, only the seat angle to be designed. So there is no need to design the seat cleat angle. So the cleat angle and nominal angle is chosen and it is placed. So cleat angle. So you will be designing the seat angle. Now sometimes the reaction that is coming to the beam to the connection is very much large. Now depending on the situation, so if we want to design the connection for this huge load, the number of the bolt will be huge. So to facilitate that much number of the bolts, an extra angle is used for seat connection. That angle is called stiffening angle or stiffener angle. When the stiffener angle is used, then the seat connection is called stiffened seat connection. In the next picture, you can see a stiffened seat connection with stiffener angle. Here also cleat angle is there, seat angle is there, but to facilitate the more number of bolts, a stiffener angle is also provided. So it is a stiffener angle. It is like two angles are connected together to form the stiffener angle. It's like that. Okay, this is a representation of the stiffener angle. Okay, two angles, this is one, two angles are joined together, which is in turn connected with this seat angle are connected here. So stiffened seat connection is one type of connection and unstiffened seat connection is another type of connection. in the seat connection design, we will design both connections, stiffened seat connection as well as unstiffened seat connection. Now, coming to the design procedure of the unstiffened seat connection. So, I have discussed what is stiffened and unstiffened seat connection. So, first we will discuss the design procedure for unstiffened seat connection. Now, as we know that the first step is the length B of the seat angle is assumed to be equal to the width of the beam width of the flange beam. That means this is the flange beam width BF of the width of the flange beam. So, the length of the seat angle will be same to that value, so it will be same. Okay, next coming to the width value. Now in these pictures we will discuss this now. So now step 2, now to determine the seat length, first the wave bearing or crippling length is calculated. The bearing, that means how much length of the seat angle is taken for the bearing of the beam. So here we can see from here, that is the starting of the beam to here. Okay, from here, this is the length of the wave bearing. Now if we want to say wave bearing, in the design of the beam we have discussed what is wave bearing. That means that we discussed that in case of the wave bearing in steel beam design, that is the wave crippling load, the load acts 45-degree angle. If we go through the lecture, you can see that in case of the wave bearing, in case of the beam, the bearing makes a 45-degree angle. So total length is the bearing. So here, from here, that is the starting point of the beam to here, that is the wave bearing length. Now that value is called B. B means length, total length of the wave bearing. B1 is the length of the bearing on seat. That means this length is taken by the seat. So this bearing, this length is taken by the seat angle. So that bearing is supported on the seat, and that length is the 45-degree angle extra value to be taken for the extra in the case of wave bearing that we have discussed in the beam, that is the crippling load. So the total bearing length will be B1 plus that load. So that is equals to length of the wave bearing B, that is the total distance, equals to R into gamma m0 by Tw by Fyw. R means where R is equal to the reaction force, that is the reaction force that is acting here, the reaction force that is the beam section is subjected to, and Tw, that is the thickness of the wave of the beam outstanding. That means this thickness, that is the Tw of the beam outstanding, that is the connected beam. So Tw have to be taken. That is the bearing or the crippling length is calculated by this formula. Now as the bearing or the crippling length is calculated, that is the value of the bearing length of the wave bearing B value. So it is the seat angle outstanding length. This is the outstanding seat angle value. This angle this portion of the angle is the outstanding length. Okay, this portion of the angle is the outstanding length. It is called outstanding length. So the seat angle outstanding length is assumed based on that, and it should be always greater than the seat angle length. So greater than the seat angle length outstanding, that is that length, seat angle outstanding length, it should be always greater than the value of B plus C. B means that wave bearing plus we have to assume some extra clearance for that. So it is very important to understand that is when we are discussing the length of the wave bearing, we are calculating the wave bearing because of we are calculating the bearing, or we are taking consideration the bearing of the wave also. Wave means the wave of our beam, connecting beam. So this is our connecting beam. So the wavelength is calculated and the bearing length of the, so this is the required length. So the length of the angle that we will use, that is the outstanding length of the angle, it should be always more than the this value, that is B plus C. So the extra clearing, that is the extra clearing here, plus the value of the length of wave bearing. So that value is calculated. Length of the wave bearing, that is equals to B. So B plus C, it should be greater than that. This is the, now based on this value, a trial section is assumed, that is trial angle section for the seat angle has to be assumed for that. Now coming to step number 3, how to determine step number 3. So in step number 3, a dispersion of 45 degrees is taken from the bearing on the seat to the root line. So this is the root line, this is the root line, and dispersion of the 45 degree, that in the case of crippling, that I have told you, in case of wave crippling we take 45 degree dispersion. So here a 45 degree dispersion is taken. This is the 45 degree dispersion. Okay, now because of the 45 degree dispersion, so B1, that is B1 means, now let us erase some of that, we do not need all that things. Okay, now what is B1, again coming to, so this is the value of B1. We have to determine the value of B1, the length of the bearing on seat. So this is the value of B1. So B1 will be this B, this is the B, total B minus that distance. Now if we draw that thing here, we can see this is the thickness of flange thickness, this is the I-beam, connected I-beam. Okay, connected I-beam, this is the flange thickness of the flange TF, and this is the root radius, this is the root length. So this is TF, so this is the TF. So TF plus R1, if we take from here TF plus R1, if it is 45 degree, it is an equilateral triangle. So this is R1 plus TF, and this is also R1 plus TF. So R1 plus TF and R1 plus TF both are given here. So if it is R1 plus TF, there it is also R1 plus TF, because it is a 45 degree angle, and that's why it is a equilateral it's a right angle triangle. For that, so this will be same to that, and because of that, the length of the wave bearing, that is equals to B1, that will be equals to B minus R1 plus TF. So R1 plus TF we can calculate, we know that from the SP6, so we can determine the R1 plus TF from here, then we can minus the value from the B1 B to get the length of the bearing on seat. This is the first value B1 to be calculated. Now, and the distance from the end bearing to the root of the angle, that means end bearing to the root of the angle, that means this is the distance of the end bearing, this is the end bearing, and this is the root of the angle. Okay, this is the root of the beam, that is the connecting beam, and this is the root of the angle. So that distance we have to determine now. How to determine that distance? This is the distance determined by B1 plus C minus TA plus RA. Now let us see that how to determine B1 plus C. So B1 plus C means, if this is B1 and this is C, so that distance from here to here, this is B1 plus C. From here we will minus what? That angle and that clearance, we are minusing that, subtracting TA, that is the B1 plus C minus TA plus RA. TA means, what is the meaning of TA? TA is equal to the thickness of the angle and the root of the angle. So if you are minusing this root length and the thickness of the angle, from this value we can get the value of the B2. Very important part. Okay, let us see it in a clearer picture. Okay, stop. Now this is the representation of that zone here. So we can see from here to here, this is B1 that we have calculated. What is B1? This is the extra clearance, this is the beam end, This is the extra clearance. This is the thickness of the angle that we know. We have assumed the thickness of the angle in this step. We have assumed the thickness. We have assumed the angle, so we can assume the thickness here also. And this is the root radius of the angle that we have assumed. So we need to find out from here to here that distance. This is B2. So how to find out B2? We can see, so if this B1 plus C, this is the total distance of B1 plus C, if from here we can subtract this thickness of the angle and this root length, that distance from the total, we can get the value of the B2. So that from here to here, that total distance from here, this portion is get subtracted, then we can find out the value of the B2. So from here we can find out the B2. So the B2, that is the distance between the end bearing, that is the end bearing to the root of the angle, is find out, that is B2 by that formula. So add all the root values to the angle taken from SP6 that I have discussed here. Okay, now then step number 4, connected leg is so chosen at least 2 horizontal rows of bolts can be accommodated. So for that, pitch value has to be known. So from here, if we know the pitch value, then we can determine the connected leg length, so that 2 horizontal rows of bolts can be accommodated in that case. Now step number 5. Step number 5 is bending moment at the critical section is determined by that formula BMC, that is equals to R by B1 into B2 divided by B2 by 2, where R is the reaction at the end, that is acting at the end. And the moment capacity of the angle is determined by the moment capacity of the angle section is determined by MD is equal to 1.2 ZD into Fy by gamma M0, where ZD, we can see that ZD is equal to the length of the angle B into TA, length of the angle B into TA square. Okay, length of the angle by TA square divided by 6. The length of the angle that we have already taken, it is equals to here in the step number 1, the length of the angle B, it is assumed similar to equals to the width of the film flange. So we know the value, we can calculate the ZD. So ZD, section modulus of the outstanding leg angle providing the bearing. Now always MD should be greater than M, that is the design moment should be, the moment capacity should be greater than the bending moment of the critical section. If not, the trial section to be rechecked. So we have to redesign the trial section if that condition is not satisfied. You have to take another trial section and follow all the procedure. Then coming to the step number 6, the shear capacity of the outstanding leg is determined by that formula B into TA. B is the length of the leg into TA, the thickness of the angle, divided by that formula. It should be greater than the end reaction, that is the load acting. Clear? Then comes the where B is the length of the angle, width of the flange and the supported beam. Okay, B is the length of the angle. Okay, so length of the angle means width of the flange of the supported beam that we have taken similar to that value. So the length of the B. So the B value we know, so we can find out the value. Now step number 7, coming to the how to connection. Bolt diameter. Now step number 7, we will design the connection of the beam. Bolt diameter is assumed and number of the bolts required to connect the seat angle with the flange of column are determined. N is equal to the N reaction by strength of the bolt. So strength of the bolt is determined. We know how to determine the strength of the bolt, that is strength in bearing, strength in shear. We have to take the lesser value, you all know that. So N is the N reaction by the strength of the bolt that is determined. The strength of the bolt determined by either shear or bearing, that we all know. And finally the number of the bolts that will be provided will be determined. And a nominal cleat angle, I have told you what is cleat angle. A cleat angle, that is this angle, this is called the cleat angle. So the cleat angle will be is not a load carrying member. I have discussed it in the earlier case. So the cleat angle will be determined. The cleat angle will be taken a nominal, normal angle will be determined. So no design for that is required. Okay, so this is the design procedure. We will see that in a math how to proceed with the design. It is very important. We will see one math of this stiffened connection. Now coming to a very important, that is the unstiffened seat connection. Why the requirement of the unstiffened seat connection? That I have told you that when the reaction force on the member is very much large, and to accommodate for that reaction, a large number of bolts are required to make the connection. Now, if the angle, if we provide only seat angle, the number of the bolt may not be provided as per the required limit. So, extra numbers of bolts are provided with the help of extra pair of angle. Extra pair of angles are used, which are called stiffener angle. Okay, which are called stiffener angle. If we see the picture here, we can see that this is the stiffener angle. This is the stiffener angle. Here the bolts are provided here. Okay, extra numbers of bolts are provided here for the extra bolt that to be provided for the high reaction force. So here an extra angle to be provided extra. So for the stiffener connection, stiffened seat connection, the design procedure is somehow different. We will discuss that now. So this is the some theory why I have discussed why we need the stiffener angle and how to provide that. That lecture is discussed here. Now coming the design procedure. The length of the seat angle B is assumed, which is taken equal to the width of the beam flange, that we have discussed in the here stiffened unstiffened connection also. So this is the length of the seat length of the angle, that is B value. We have to take that first. Then coming to the length of the bearing for the seat angle is determined. What is the length of the bearing? That I have told you in the previous unstiffened connection also. From here to here, this is the length of the bearing for the stiffened seat connection. The length of the bearing is calculated. The formula is same: R by TW into gamma M0 into FYW. R is equal to the reaction force and TW is the thickness of the web of this beam. Okay, very much clear. So thickness of the web of this beam. Now from there, the outstanding leg length of the seat angle is determined as outstanding leg length. It should be greater than B plus C1. We have discussed that in the previous procedure also, that the outstanding leg length should be greater than the B plus C1 always, where C1 is the extra clearance to be provided. This is the extra clearance C1. I have discussed that we have to assume some clearance here so that the clearance can be provided between the beam and the column flange, so that conditions to be satisfied. Now a suitable angle section is selected based on that. It is the same as the previous procedure. Now coming to the outstanding leg of the stiffener angle must provide required bearing area. Outstanding leg of the stiffener angle must provide the required bearing area. It is we have to ensure that the required bearing area, so that the beam is properly placed on the angle. So the load coming from the beam, the bearing of the beam, the angle should be so chosen that that angle should be sufficient, so that it can take the bearing should have the sufficient area so that it can take the bearing coming from the beam. So the required bearing area is calculated by A is equal to R into gamma M0 by Fy, where R is the reaction force from the beam, reaction force that is coming from the beam. Okay, now reaction force is coming from the beam, which should be always less than 14 into TA into epsilon. That means 14 into thickness of the angle into epsilon. That has to be, it should be always less than that. That has to be checked. Next comes the value of the eccentricity we have to determine here. As we are using the stiffener connection, value of the eccentricity we have to determine. The eccentricity, that reaction, the eccentricity, that reaction that is coming from the beam, eccentricity, that the reaction coming from the beam is taken to be acted at a distance equal to bearing length by 2. That means the load is acted here. So where the eccentricity will act, it will be acting as a distance Ex equals to length of the outstanding leg by 2. Why we are taking the value of Ex here? So that here a stiffener angle has to be also used. So we need to be concerned, we need to be confirmed about what will be the length of the Ex, that is the eccentricity that to be provided. So the length of the eccentricity has also to be determined here. So the length of the eccentricity is determined by this value. The length of the outstanding length by 2, the Ex, that is the eccentricity, will be determined by that formula. Now coming to step number 4, design of the connection of stiffener angle to column flange. So design of the connection of the stiffener angle to the column flange. As I have told you, the stiffener angle is connected with the column flange and the seat angle is provided. So the stiffener angle connection has to be determined. So the connection of the stiffener angle is determined by this procedure. Dia of the bolt is determined, assumed the pitch and the edge distance are assumed. The strength of the bolt in double shear. Why it is double shear? If we see this picture, all right, let us stop. Now you can see this is the stiffener angle. Okay, this is the stiffener angle. This is the seat angle that is connected, and this is the column flange. So it provides a butt connection here. So as there is a butt connection, so the strength of the bolt in double shear has to be determined. So as there is a butt connection, if you see this picture, it will be much more clear to you. This is the stiffener angle, this is the seat angle, this is the column flange, and this is the extra packing to fill up the gap. So here it is always a butt connection is acting here. So always a double shear has to be determined. Therefore bearing and the tension is determined also. From there the strength of the bolt is determined. So that we have to take the strength for bearing, strength for shear, and here also strength for the tension, because we are taking the value of the eccentricity also. So the moment will come, we have to design for the moment also. So as the eccentricity we are assuming here, we have to also consider the tension force also acting here. So the tensile tensions, the strength of the bolt in tension also need to be determined. Then here the number of the bolts are determined by this formula, that is root over of 6m divided by P into N dash into VSD. What is M? M is the R into eccentricity. R means the reaction force, and eccentricity value we have calculated here. Eccentricity, we can take that. M. VSD, design strength of the bolt, we have calculated the design strength in shear, bearing and tension. From here we can determine the shear strength of the bolt, that is the least value from all of that. And then N dash, that is the N dash is the how many rows of bolt are there. If there are 2 rows, there generally 2 rows are provided. So for 2 rows number will be 2, for 3 rows number will be 3. So this N, this is the number of the bolts in only 1 row. So here we are calculating the number of the bolt in only 1 row only. So we can see if this is a stiffener angle, in this picture this is the stiffener angle, this is 1 row of bolt, this is another row of bolt. So 2 rows are provided in general, but if we require maybe more than 2 rows also can be provided. So 2 number of rows are provided. Now this is the step. So number of the bolts in only 1 row are calculated. So if there are 2 rows, so this number will be multiplied by 2 when to calculate the total number of bolts. Now the shear and tension at critical bolt is calculated. Critical bolt means, what is the meaning of critical bolt? Critical bolt is the bolt which is farthest in the bolt row. Here this is the farthest bolt in the bolt row. This 2, if it is 1 row of bolt, if this is 1 row, this is the farthest bolt in the bolt row. This is the farthest bolt in the bolt row. So we have to determine the shear and tension for this bolt. How to determine? The shear force in the critical bolt is determined VSB. Reaction, that is the value of R that we know, value of R. Reaction, that is the value of R we know, R, and number of the total bolts, that is 2, that is how many rows are there, and number of the bolt in 1 row. So if there are 2 bolts, 2 rows, 2 into n. If there are 3 rows, 3 into n, that we need to determine. And coming to the very important portion, tensile force at the critical bolt. Tensile force, when we are determining the tensile force TB, it is determined by this formula, m dash into yn divided by summation of yi square, where m dash equals to m divided by 1 plus 2 into h by 21 into summation of yi by summation of yi square. Okay, I will discuss all the terms present here. This is the formula. Now coming to how to get that thing. Okay, what is the value of m? This is m. M means reaction into the eccentricity. This is that value. M we have calculated reaction into eccentricity. So we are putting the value. H is equal to depth of the stiffener angle minus the edge distance. So we have calculated the edge distance here. So from here, this is the edge. If we see clearly here, if this is the stiffener angle, from here to here, this is the value of the edge. This is the total length. This is the total length, and from here the depth of the stiffener, this is the depth of the stiffener. From here the edge distance is divided. Edge distance we have calculated, minimum edge distance. From here, when we are designing the connection, we have to take the edge distance. So edge distance is calculated. We have to divide, subtract this edge distance here. So we are getting from total that edge distance is subtracting when getting the value of edge. Now why is the requirement of the edge? Edge is required here, and also we have to take the value of the yi from here also. Now the rotation center, now as the tensile force and the moment is acting in the stiffener angle, it is taken that the rotation angle, that means where the moment will act. That is the very important part. Where the moment will act, it will be positioned at a distance h by 7 from the bottom of the stiffener angle. That means the rotation center for stiffener angle is at a distance h by 7 from the bottom of the bracket plate. So if this distance is h by 7, if this distance is at h by 7, so at that distance, the rotation center will be present. This is the rotation center. Now why we need the rotation center, we will discuss it now. Y, this is yi and yi square. Y equals to distance of the rotation center, distance of rotation center to the center of the bolt above rotation center. That means, very much carefully listen, that is, if this is one bolt, this is another bolt, this is another bolt, that bolt will not be considered because that bolt is below the rotation line, rotation center. So that bolt will not be considered. So y1, that is the distance between that rotation center to the center of the bolt. This is the value of y1. What is y2? That rotation center and the distance between that y2. And I have told you the farthest bolt, this is the farthest bolt from the rotation center. So this is the critical bolt. Okay, so this is the critical bolt. Okay, critical bolt. So the distance between the farthest bolt from the rotation center is yn. So this is yn. That is the distance between the farthest bolt from the rotation center. So summation of the yi, that is the y1 plus y2 plus dot up to yn, and yi square, this is the yi square, that is equals to y1 square plus y2 square plus yn square. Okay, so y1, y2 and yn, and y1 square plus y2 square plus yn square has to be determined from that formula. By that concept, why it is y1, why it is y2, why it is yn. I think it is clear to you why it is y1, why it is y2 and why it is yn. We have to determine from that formula. So putting all the values here, we can calculate the m dash, and then from m dash to tb. Now that tensile force in the critical bolt and the shear force in the critical bolt is calculated. Now finally the connection is checked for the combined action of shear and tension. So combined action of shear and tension, when we have discussed the bolted connection, we have discussed the combined action of shear and tension. When the moment is acting, here the moment is acting because eccentricity we are considering. So the moment is acting. So though That's because the moment is acting here, the connection to be checked for combined action of shear and tension, that is the VSB, that is the strength of the bolt in. So VSB we have calculated, that is the shear. VSB we have calculated, that is the shear force at critical bolt, divided by VDSB, that is the design shear force of the bolt, VDSB, and TB, that is the tensile force of the TB, that is the tensile force at the critical bolt, that is TB. We have determined tensile force at the critical bolt divided by TDB, that is the design tensile force of the bolt. That value, the ratios, that formula should always be less than 1. If that condition is satisfied, then the connection is to be okay. So this is the theory. This is the theory for the design principle for un-stiffened seat connection. In my material, stiffened seat connection math hasn't been shown. I will give one give one assignment in your homework, so that you from the book, so you can do the math by yourself, and it will be clear to you why these things are used. Next, coming to the math. That math is based on the un-stiffened seat connection. Design a seat connection for a factored beam. End reaction 110 kN. Beam react section is ISMB 250. That connected with the flange of a column ISHB 200 using bolted connection, grade number ATO and ATO. So it is a seat connection. Okay, so as the load value is less, only 110 kN, we do not need to design it for stiffened seat connection. We will design it by un-stiffened seat connection. So let us use the formulas here. Now coming to the design procedure. Okay, so this is the design procedure for stiffened seat connection, I think. Un-stiffened seat connection. So you use un-stiffened seat connection formula. So first, the length of the B of the seat angle is assumed. So the end reaction is equal to 110, we know. So writing all the properties of the ISMB 250 and ISHB 200, that is the two properties are here. Flange, this is the column, and this is the beam. So their values are here. All the value written. Now length B of the seat angle. So length of B of the seat angle equals to width of the beam flange. So for beam, that is the ISMB 250 is the beam, ISMB 250 beam section. So width of the beam flange is equal to 125 mm. So B is equal to taken as 125 mm. Clear? So first step is done. Next, step number 2, we have to determine the length of the wave bearing B. So wave bearing B, length of the bearing B is calculated by that formula, R into gamma m0 by TW into FYW. Now TW is equal to 6.9 because ISMB 250 having TW is equal to 6.9. This is the wave of the beam connected. So putting the value, we are getting 70.14. Now what is written here? If we okay, the seat angle, the outstanding length of the seat angle is assumed based on that, and it should be always greater than that value. So seat angle length outstanding should be greater than B plus C. So assuming outstanding length of the seat 75 mm. We are assuming the outstanding length of the 75 mm. So and providing 3 mm clearance. So the value of this C, consider this is 3 mm only. So B plus C, B is 70.14 plus C, that is 70.14 plus 3, that is 73.14. It is less than 75. So it is required length of the outstanding, that is that value. It is greater than, it is less than seat length, that is 75 mm. So it is okay. Now we have to assume some angle for that value. So let us open ISSP 6. Let us check one angle which has this 75. So we can take first, let us check that value 125 into 75. Okay, let us take 125 into 75 into 10 ISA. Let us take 125 into 75 into 10 ISA. This is the length of the outstanding leg. 125 into 75 into 10 ISA we are taking. So we have taken the angle. So now check step number 3. Step number 3 is dispersion of 45 degrees is taken. Why you know this is for the wave tripling function. Now B1 equals to B minus R1 plus TF. So B1 equals to B capital small b minus R1 plus TF. R1 means 70.14. That is the B. We have calculated B value is equal to 70.14 minus R1 plus TF. R1 means what is R1? R1 is What is R1? R1 is the R1 is the root length of the beam. So for the beam, R1 is 13. So putting the value here 13 plus, that is the R1, that is the root length. For the ISMB 250 is 13. So putting the value here 13 plus 12.5, 44.64 mm we are getting. Okay, 12.5 the thickness of the TF is the thickness of the flange of the beam, that is the 12.5 we know. Now the distance between the end bearing to the root, that is B2, you have to calculate. B2 formula is that formula. We know B1, we know C, we know TA, we know RA. RA is the thickness of the angle, that is 10. So putting all the values, RA, thickness of the angle, that value, it is calculated, thickness of the angle. And RA, what is the RA? The root length of the root length of the angle. So for IS 125 into 75, the root length is IS 125 into 75 into 10, that is that value, I think. 125 into 75 into 10, last one. So for the last one, 125 into 10, that is last one, the value of the root length equals to 9. That the radius of the root, that is equals to 9 mm. Okay, so putting the value here, so 9 mm we are taking. So R1 is equal to 9 mm. So 10 plus 9, we are getting the value of B2 is equal to that. Now coming to the bending moment at a critical section. So step number 5, base MC, that is equals to bending moment at critical section, R by B1 into B2 square by 2. Putting all the value, it is coming to 1010 kilonewton meter. MD, that is the design moment capacity, that is coming to the 1.2 ZEFY by gamma m0. Z is equal to length of the angle. What is the length of the angle we have taken? That is 125 mm. We have taken the B is equal to 125 into TA, thickness of the angle, square by 6. Putting all the values, we are getting 568.181. Here MC greater than MD, but we have to make MD greater than MC. So MD greater than MC, that is the value we are getting, MD greater than MC. So the design has to be redesigned. So taking another angle. What angle to be taken? Consider we are taking some greater angle, that is 150 1 to 75. That angle of having thickness equals to 12. 170 into 75 into 12. Higher thickness we are assuming 12. 170 in 150 into 75 into 12. We are assuming that section. So for 1750 into 75 into 12, B1 we are calculated value is same. B1 equals to 44.64. B1 will not change. B1 equals to that value. It is not changed because it depends on the R1 and TF of the beam. It is the beam section, so it value will not change. B2 equals to, now coming to B2 for MD. Now for 150 75 into 12 for here, 150 75 into 12 for here, the B2 equal the issue is equal to 10. Okay, so we are putting the value RA equals to, that is the RA equals to 10 here, and thickness here, so 25.64 millimeter is the value B1 by B2. So MC is equal to the critical moment equals to 809.98 kilonewton meter, and MD is equal to 818.18 kilonewton. Putting all the values here, so MD greater than MC. So the design is now satisfied. So first condition is satisfied. So next, coming to the step number 6, shear capacity of the outstanding link is determined. So shear capacity is VDP, that is that formula. So beta B into TA, B is equal to 125, T is equal to thickness of the angle, that is 12. Putting 250 to gamma m0 196.82, that is greater than 110 kilonewton, hence okay. Next step number 7, design of the connection. So the bolt will be in single shear, as the connection is in single shear, because when it is a angle section, normal angle, so here only lap connection is provided, so the bolt will be in single shear. So single shear connection will be designed here. So when the bolt will be in single shear, then the bolt providing 20 mm diameter bolt, A and B is equal to 245, that we know the value. So for BDSB 45.26 kilonewton, we are getting the value. Now strength of the bearing is not checked, as it will be always more, because strength of the bearing is always more in case of if the bearing is in shear strength. So number of the bolt required will be that value 110, that is the value of the reaction divided by the end reaction by the strength of the bolt, is that is equal to 2.40. 4 numbers of bolts are required. So provide 4 numbers 20 mm 4.6 gauge bolt in 2 rows to connect the seat angle. So if we see that picture here, so 4 numbers of bolts will be provided here. So if we draw a picture, we can draw a picture here. So if this is the seat angle, four numbers of 2 rows, 4 numbers of 20 mm diameter bolt in 2 rows, like that. This will be the seat angle connection provided. Now, as I have told you in the step number 8 that we have discussed, that is in step number 8, a nominal cleat angle is provided in the top of the flange. So nominal cleat angle we can take a nominal angle. A nominal angle is taken in the higher side. I will always suggest to take an angle on the higher side. We are taking an angle 100 into 75. 100 into 75. Okay, always try, it's my suggestion that always try so that the cleat angle length also same as the cleat angle length, and the cleat angle leg length, outstanding leg length is same as well as the seat angle. As we are taking the seat angle length 75 length, so the length of the cleat angle is also taken 75. So 100 into 75 into, you can provide 10 mm. So I am providing here 100 into 75 into 8 mm. So as a cleat angle over the top of the flange. So this is the connection for the seat design of the unstiffened seat connection. Now the stiffened seat connection will be done by the formula I have discussed. So we will one math I will give you as an assignment, and you will try to do that by the formula. Now coming to the bracket connection, very important connection. Bracket connection are very much provided, and this is, you can see that connection everywhere. Okay, bracket connection are provided when two members to be secured together when subjected to direct shear and shear due to torque. Okay, so two members are connected together. This is the bracket plate. Okay, here there are generally two type of bracket connection are provided. In the picture you can see, if we see in the picture, you can see there are generally two type of bracket connection are provided. This is the bracket connection type 1 and bracket connection type 2. So two type of bracket connection is provided. In the bracket connection type 1, a bracket plate is provided here like that. Okay, bracket plate is provided. This is a column flange. A bracket plate is provided here, and the bracket plates are provided here, and the load is acting here. Okay, this is the load is acting. That means the load due to another member is placed here. This is the bracket connection type 1, and the second bracket connection is like that. When a bracket plate is provided like that, and extra angle like that, a bracket angle has to be provided to connect the bracket plate with the column flange. Sometimes a bracket plate is like a T-section. T-section is provided as the bracket plate also, like that. Okay, T-section is provided at the bracket plate also. So here there will be only one row of bolt. Okay, only one of these. So this portion is not required for that. So sometimes T section is also provided for the bracket. Okay, so this is the bracket connection types are here. So we will try to discuss the design for the bracket connection type 1 and the bracket connection type 2. First, the step. The diameter of the bolt very much easy. The steps are for the bracket connection steps are quite easy. We will discuss that. The number of diameter of the bolt are required to each pitch and gauge length are determined. It is similar for the each and every case. Then the strength of the bolt is determined in the single shear and bearing. Single shear because it is in the single shear because it is always a lap connection. It is for that we are discussing the connection of the design procedure for bracket connection type 1. So this is always in the lap joint, not a butt joint. So always it will be in the single shear and bearing. The number of the bolts are determined from that formula that we have discussed, that is a 6m by p into n dash into bsd. Now what is the m is the end reaction into the eccentricity, p into e0, m is equal to end reaction into the eccentricity, that is the p into e0 that we have discussed. We are in reaction into e0. Here you can also see this is the end reaction in the e0, p0, and n dash equals to number of the bolt rows, 2 for 2 rows generally we are taking. It is same in the case of the stiffened seat connection design. V is equal to the design strength of the bolt that is calculated. Okay, step number 2, that is resultant force on the critical bolt. What is the critical bolt? The critical bolt here also, the bolt which is at the farthest position. which is as the farthest position. It is the resultant force of the critical bolt is determined. So the formula for determining the resultant force is equal to that formula. Okay, resultant force determined by this formula. So F is equal to F1 square plus F2 square plus 2F1 F2 cos theta. We will discuss all the parts later. Now F1 is equal to P by N. P means P is equal to number the reaction force, eccentric load that is acting, and total number of bolts calculated. So N equals to, here the N, the number of the two rows here. So two rows, so number N will be multiplied with 2. If number of bolts are 3, the number of rows are 3, so multiplied with 3. So two numbers of bolts, so now N is the number of the bolts calculated. So F1 we have calculated. F2 is equal to AP into E0 into Rn by summation of R square. E0 is equal to the eccentric distance that we know, that is the eccentric distance E0. Okay, now sorry, Rn. What is Rn? Distance of the critical bolt from the center of the rotation. If the connection is a bracket connection like this is the visual representation of the bracket connection, type 1 connection. This is the rotation center. So this is the distance from the rotation center to the critical bolt Rn. You can see this is the rotation center, distance from the rotation center to the critical bolt Rn. So here we can determine the value of the Rn from here to here. We can determine the value of the Rn. This is the Rn. So Rn will be that distance and that distance. If we know these two values, we can determine the value. So A square plus B square. A is that value and B is equal to that value. So what is A? A and B. If we know the value of A and if we know the value of B, then we can calculate. If we can determine this pitch length, if we know the value of this pitch, we can also determine the value of the we can determine the value of this B, and A value will be given to us in the math. So A and B we can know, and we can put the values to determine the Rn. Now what is the summation of R square? Summation of distances from the center of the rotation to the bolts. So for consider these bolts, this is R1, this is R1, this is R2, this is R3, this is R4. Okay, so R1 plus R2 plus R3 plus Rn, a whole square. And so this R1, so if we know this pitch and A, we can calculate R2. If we know this pitch and that distance A, we can calculate R3. Similarly Rn. So all the values will be put here. Summation of R square will be R1 square plus R2 square plus R3 square Rn square. So that formula we have calculated the value of summation of R square. And what is cos theta? If the theta is the angle between the Rn and horizontal plane, that is that plane is the horizontal plane, and Rn is, this is the theta angle. So cos theta is equal to A by Rn. That is, cos theta means base by hypotenuse. If this is theta, this is the base, this is the hypotenuse. So A by Rn is the cos theta. Okay, so all the values can be calculated. Put all the values. So now the strength of the bolt, that is the check, the strength of the bolt should be always greater than the value of the F, that is the resultant force. So the strength of the bolt will always be greater than the resultant force that we have calculated, the resultant force F. If it is not, then the section to be redesigned, the section bolts to be redesigned. Now let us see an example. Design a bolted bracket connection to support an end reaction of 400 kN. The eccentricity of the end connection is shown in figure below. So this is the eccentricity shown. Steel used is Fe410. All the things are given. So the load is acting at a distance 250 meter. So E is equal to 250. So E is equal to 250. It is written here in the lower portion, that is E equals to 250 mm. And here you can see that 400 kilonewton load is acting at the center of the two bracket plates. So each bracket plate, the load will be divided into 400 by 2. I have written here also, as per the diagram, the 400 kilonewton load will be divided into two brackets. So each bracket will be designed for load 400 by 200 kilonewton. It is evident, we can see from here. Now coming to the step number 1. What is step number 1? Now for ISHB 150, ISHB, so what is step number 1? Let us open now step number 1 for this case. Step number 1. So Now we are assuming step numbers, going through step number 1. So step number 1 we are now taking. So step number 1, the diameter of the bolt are required. So diameter of the bolt we are first assuming. So for ISB, so writing all the properties, G90 TF 9 mm, assuming 20 mm diameter, 4.6 square volt. So D0 is equal to 22, D 20 plus 2 we know, E is equal to 33, which is the least value. So minimum value providing E is equal to 40, and 2.5 into T 50 mm providing 60 mm, and A and B to 45, that we know. So the strength of the bolt in single shear, that formula getting 45.26, putting all the values. KB is the, now we know that VDPB, that is the bearing strength, will be less greater than the VDSB, but calculating all the values 0.6166, you know all the calculation, putting all the values. Now here T will be here T will be as, this is the thickness of the gusset plate and the thickness of the flange. Now thickness of the bracket plate is not, thickness of the bracket plate is 10 mm, very much important part here. Thickness of the bracket plate is 10 mm, and thickness of the collar beam flange, it is TF is equal to 9. So what value to be taken? 9 mm to be taken. So TF less than T of the bracket plate. So 2.5 KB into D into T into FU by gamma MB, putting all the values, we are getting 90.036. Now design strength of the bolt, the design strength of the bolt will be that value, because this is a lesser value. So we'll be taking the value 45.26 kilonewton. Number of the bolts in each row, now you have to determine, putting all the values in each row. So 8 number of bolts will be in each row. So 8 number of bolts in each row, taking n dash equals to number of rows 2 as provided. So we are providing 2 number of rows, 2 number of rows, in total rows number are 2 we are providing. So in each row 8 number of bolts are there. So this is the diagram of the bracket connection. This is the diagram of the bracket connection. So each rows, so 8 numbers of bolts are there, and edge distances are also provided 40, 60, and this is the bracket connection is that, like will be like that. Okay, now calculation of the, now coming to the next step, that is the resultant force. So P1 is equal to P by F1 is equal to P by N. So this P is equal to 200 by 16. 200 is the applied load in one bracket. So 200 by 16 will be the, as each row has 8 bolts, total number of bolts is equal to 16. Okay, total number of bolts is equal to 16. F1 is equal to 12.5 kilonewton. Now F2 we have to calculate. F2 is equal to P into E0 by Rn by R square. Now Rn equals to, from here to that distance equals to Rn. This is Rn. This is the value of Rn. So Rn equals to that distance. Now in the math it is given that distance equals to 90 mm. That distance 90. So from here to here, it will be 45. Okay, so value of A equals to 45. It is shown here also. Value of A is equal to 45, and value of B, that is from here to here, that is equals to here, that is 60, 60 and 60, that is 180, that is 3 into 60. 3 into 60 it is there. So 3 into 60 plus 3 into 60, that is from here, from here to here, and from here to here it is 30. This shown here, that is 30, because that distance, if it is total 60, so if the moment rotation center is here, so it will be divided in 2 parts, 30 30, so that distance is covered. So Rn equals to, putting all the values, we are getting 214.77. Now calculating of the R square. So first R1, this is R1. Now very important thing here, 4 into all the values. Why 4 into? Because if this is the moment center, then this is R1, this is also R1, this is also R1, this is also R1, this is R2, this is also R2, this is also R2, this is also R2, this is R3. So it will be same. So 4 number of all the distance will be taken here. So 210 square plus, so first R1 means that distance and that distance, so square of that distance and that distance is 45 square plus from here to here square, that is 45 square plus 30 square, that is the that here to here. Next from here to here, that is 45 square plus 60 plus 30, 45 square plus 30 plus 2 into 60, and for that the Rn equals to that value, so putting the value, so we are getting R square is equal to 334.8 millimeter square. Putting all the values here, we are getting summation of that. So F2 will be equals to putting all the values of AP into E0. E0 is equal to it in the given, that is 250 mm is the E0. So putting all the values P into E0, we are getting 32.074 kilonewton. So cos theta, and cos theta will be equal to theta is equal to that distance, that value is equal to theta. So A base by hypotenuse, A by Rn, so A is equal to 45 and Rn is equal to that distance. So putting the values, 0.209 is the value we are getting. So F is equal to 36.77 kilonewton. So VDSB we have get it 45.126 kilonewton, which is greater than that 36.77 kilonewton. So the design is okay. This is the very much easy and very much easier process to calculate the design strength, the design of the normal bracket connection type 1. Now coming to bracket connection type 2. When the bracket connection type 2 is provided, it is written here, when the moment in the plane perpendicular to the plane, when moment is in the plane perpendicular to the plane of the connection, the bracket connection 2 is selected. If we go in the bracket connection 2 picture, here the load is acted and the moment will act in that direction. So the moment is acting in a plane perpendicular to the plane of connection. So this is the plane of connection and the moment is acting perpendicular to that plane. So bracket connection will be provided, bracket connection type 2 will be provided here. Design procedure is somewhat similar to the unstiffened seat connection. Throughout the design procedure we will see that it is similar to that unstiffened seat connection. Okay, first the dia of bolt is assumed like the first procedure that is here. Okay, so we will now see the procedure. First the dia of bolts is assumed. What it is? Okay. Dia bolt is assumed, pitch and gauge distance is assumed, strength of the bolt in calculating single shear and tension. Okay, it will also be in single shear. If we see the picture, here single shear is on, it will also be in the single shear, not double shear. Always the single shear for bracket connection. So single shear is calculated and tension. Then the number of the bolts in the each row is calculated by that formula. So for each row the number of the bolts are calculated by that formula. Okay, then the dimension of the bracket plate is determined. The dimension of the bracket plate. Here, the dimension of the bracket plate will be determined. Okay. Now, if this is the bracket plate, if we know the number of the bolts in each row, we know the pitch distance, we know the edge distance, we can determine the size of the bracket plate also. Now, shear force in the critical bolt. Critical bolt is the bolt which is at the farthest distance, the critical bolt, which is similar to the unstiffened seat connection. So shear force in the critical force is determined by P is equal to number of the total bolts. So if 2 rows are there, 2 into n value will be taken here. So number of the total bolts. Tensile force in the critical bolts is calculated by this formula. This is similar to that formula. I have discussed what is M, what is H. It is similar in case of that also. Here also the H is equal to depth of the bracket plate minus the edge distance, that is the depth of the bracket plate, that is the H, that is the depth of the bracket plate minus the edge distance. So total depth is H minus the edge distance is the H value. Now in case of the bracket connection type 2, the rotation center, that is rest at a distance h by 7. It is also similar, h by 7 distance it will be placed. So y is equal to distance from the rotation center to the center of the bolt. So this is y1, from here this is y1, this is y2, and this is at the end, this is as equal to yn, that is a critical bolt. So y1 is equal to y1 plus y2 plus yn, and yi is equal to y1 square plus yn, or yn is equal to, we know that distance from here to here is the yn. So we will calculate the value, then we will put the check for the combined action of the shear and tension, because here moment will be acting because of as the moment is parallel to the plane, the moment will be acting here. So we have to check the design, the bracket plate, for the combined action of tension and shear. So the tensile strength of the bolt and the tensile strength of the critical bolt and the tensile strength of the shear strength of the critical bolt is calculated based on that formula, and then the check is done. Always it should be less than 1.0. So this is the general procedure. We have done this procedure. Now we will see a math. Okay, so let us do the math. Okay, how much time is there? 1 minute 28 seconds. Okay, one hour is over. So we will start with the math, that is the given p value. So let us come to the design procedure. What is the design procedure? Okay, the design of the bolt is assumed. So P25 E is equal to 300, that is given, the 300 milliNewton from the column flange. So this is the picture. So 300 kilonewton column flange, 225 kilonewton is the applied load, and this is the T bracket. So this is a type 2 bracket connection. So we will design that type 2 bracket connection by this. So assuming dia of the bolt 20 mm dia, A and B 245, E minimum 33, we are taking 40, 50 we are taking 60, strength of the bolt in single shear calculating, strength of the bolt in tension. Now strength of the bolt in tension is equal to TDB. We know that TDB is the formula for TNB by gamma NB. Now TNB is equal to 0.9. This is only TNB. This is only TNB. 0.9 FUB into ANB. 0.9 400 into 245. This is equal to 88.2 kilonewton divided by gamma MB. Gamma MB 1.25. That is equals to 70.56. Now TNB should also be less than FYB, gamma MB, ASB, gamma MB. ASB is the shank area, pi by 4 into 22 square. So pi by 4 into 22 square. So we will check that, and it will be always less than that value. So the number of the bolts required is equal to 8.66, or 9 number of bolts are required here. So providing 9 numbers of bolts like this. Okay, let us zoom a little. So 1 2 3 4 5 6 7 8 9. So 9 numbers of bolts are provided here. So 9 numbers of bolts are provided. So then the step is dimension of the bracket plate is calculated, the depth of the bracket plate. So depth of the bracket plate will be 8 into 60, because 60 is the pitch, plus 2 into 40, because 8 into 60 plus 2 into 40. So this is the depth of the bracket plate A, that is equal to 560 mm. Now step 3, shear force in the critical bolt FSBSB is equal to that value 12.5, 225 into 18, calculating all the values. Tensile force in the critical bolt equals to H, that is equals to 560 minus 40 is equal to 520. H equals to VSB we have calculated. Now H means, what is the meaning of H? That we know that is the depth of the bracket plate minus the H distance. So total depth of the bracket plate is 560 minus H distance 40, calculating the value 520. Rotation center lies H by 7 distance, we know that is 74.2 meter. Okay, so rotation center lies 74.2 meter 29 mm from the bottom of the bracket. So now coming to the yn it will be equals to, from here to here, this is yn, from here to here this is yn. So putting all the yn is equal to, so total H, this is the total H minus 74.29, total H minus 74.29, we can get the value of the H minus 74.29 is the value of the yn. So yi we have to calculate. So y1 equals to, from here to here distance. So how to calculate the yi? See, if this is, consider this is the first bolt, this is the H by 7, and this is the, in this picture this is H by 7, from here to here this is 60. So if we can add, and this is here to here, this is 40. So 60 plus 40 minus H7, that is equals to the distance between that rotation center to that value. This is y1. So 60 plus 40 minus h1, h by 7, putting a value here. So first for that, the second bolt it will be plus 60, here will be that another 60, it will be y2, so plus 62 into 60, 3 into 60, so getting up to 18 to 60. This is the last bold. Okay, this is the last bold. Similarly, we put in all the values, we are getting yi is equal to 3771.36. Similarly, yi square is equal to value of all the square to be summation all together and getting that value. Here only 2 rows of bolts are being a T bracket, no need to calculate extra bracket angle, that we know for a T bracket. Now as it is a T bracket, this is a T bracket, there is no need of extra bracket angle to be provided. So in this picture that I have told you also, that in a bracket connection sometimes T bracket are provided, so there is no need of that angle connection, only a T section is sufficient, so no angle is required for that. So as no angle is required for that, putting all the values here, getting T m dash equals to 58.35 into 10 to the power 6, 58.8 was 3 kilonewton meter. Putting value of the TDB, we are getting 21.83. So value, putting all the values of next last step from step number 5, putting all the values of BDSB, BDSB, TAB and TSB is the strength of the bolt in shear and strength of the bolt in tension that we have calculated. Putting all the values here, we are getting 0.17 is less than 0.1.0, hence okay. So up to today's lecture is very much important, and that's why it's a long lecture. Why? Because the eccentric connection is very much important for your study. Today we have discussed only, we have discussed the bolted bracket connection and how to design all types of bolted bracket connection. We have discussed all the design steps, we have discussed all the design procedures, and then we have seen some of the maths to be done. Okay, so examples we have done. So the bolted bracket connection up to this. So this is the bolted bracket connection, and all the lectures have been given to you. Now if it is possible, I will discuss the class also in the Zoom live video if it is possible for me. But up to this is the bolted bracket connection, and it's very much important how to design the bolted bracket connection. And I will urge you to start studying for your semester also, because the exam will start at when the college will open. So please start your study. Okay, so up to this is today's lecture. In the next lecture, in the next class, we will discuss welded eccentric connection, eccentric connection with the welded connection. Today is the bolted connection. Next we will discuss the welded connection. Okay, up to this is today's lecture. Okay, thank you very much.